need to consider, is that pathogen susceptible to this drug? We have to measure how effective the drug is going to be, the efficacy of this drug. Again, I can have a great drug that doesn't harm the host, but if it doesn't do anything to our pathogen, if it doesn't inhibit, if it's not toxic to the pathogen, it's not a good drug for that. This should look familiar to you. This is that Kirby-Bauer test, that antimicrobial susceptibility test that we did in lab. I'll let you review that on your own. Remember, we used that Mueller-Hinton agar. We streaked out bacteria. We used a disc soaked in a different antimicrobial, so we had a dosage for that. And then we looked for that zone of inhibition. Did it inhibit the growth of bacteria? We always had to measure that to a known chart to determine whether the bacteria is resistant to the drug. So this would be, this bacteria right here is resistant to this drug, or susceptible, or somewhere intermediate. And again, we couldn't just base on the size of the zone of inhibition. We need to compare that to a chart. So you can review how that worked. So efficacy. Zone of inhibition tells us whether it's susceptible or not. Now, there is another test. Not only do we need to know, is this bacteria susceptible to the drug that I want, but I also need to figure out what type of dosage I need. I want to use the smallest dose that will do what I need it to do, inhibit the growth of the pathogen, because the smaller the dose, the less chance that it will harm the host. Selective toxicity. I want it to kill the bacteria, but the smallest dose will allow it to have the least amount of side effects, the least amount of chance of harming my host. All right, so how do I figure that out? We need to determine the MIC, and we talked about that in the Kirby-Bauer test too, the minimum inhibitory concentration. When we talked about it in lab, I'll go back, we said that the area, the zone here is the zone of inhibition, but this circumference is defined as the minimum inhibitory concentration. The minimum concentration needed to inhibit the bacteria. On this side, in the zone of inhibition, this dosage inhibits the bacteria. On this side, this dosage does not inhibit the bacteria. So right at this line is the minimum inhibitory concentration. And we mentioned we need to do that so we don't have side effects. All right, so how do we determine? We can't really determine on the Kirby-Bauer. You can do this broth dilution test. And so we start out with a certain dosage. This one is 50 micrograms of a drug, and you can see it inhibits the growth of the bacteria. So this dosage works. And they're going to do serial dilutions, which means we're going to dilute it by half. With every one, so 50 to 25 to 12.5 to 6.25, and we're going to go through, and then each of these dosage is sufficient to get rid of the bacteria. This one is sufficient. This one is sufficient, and then when I half it again, we can see now I got growth. So my minimum concentration that inhibited the growth is this last clear dilution, my minimum inhibitory concentration. Vocabulary, when we see this cloudy, remember that's turbid. All right, so this is a way that you can determine the MIC, the minimum inhibitory concentration. Now, drug companies are smart, and we are continually doing new things. There is something called an e-test that combines these two tests. We can do our Kirby-Bauer, where we take a strip and put it on there, but this strip, instead of being one single dose from that, it's actually a strip that has these dilutions. So here's where the drug is the strongest, but then each one of these is a serial dilution, and you can find the minimum inhibitory concentration. That's going to be where the MIC, the zone of inhibition, or the minimum inhibitory concentration, crosses this. So that's a test that can do that. All right, these are tests that we use because we need to determine if the drug works. That, again, back to selective toxicity, this overwhelming desire, we have to make sure that this drug works against the pathogen. And we have to make sure that it does not harm the host. Everything else is gravy. So just to give you some concepts, we're talking a lot in the media right now with COVID-19, and there's lots of talks about drugs that will work against this virus, and there's lots of talks on that. The scientists, the doctors, are a little more cautious. The politicians may be a little more saying, oh yeah, this is going to be great. Scientists know that we have to do the tests. Just because a drug is safe in one population doesn't mean it's safe to be given to a different population, meaning a population that has this virus. That can completely negate the safetiness. A drug that works for one disease may not work for the other disease. And the fact that these patients have this virus may give us some unintended consequences, some unintended side effects. So we have to test it, you know. So this process does take time, and I know it gets frustrating to do it safely. But you know, that's the best thing we do. Overall, physicians want to do no harm to their patient, and you get the thought that, well, if these patients are sick anyway and they're going to die, you know, yes, that could be something else that can add in there, but it's very difficult to have that. To carry that weight that something you did as a caregiver hurt that patient. So that's why physicians and scientists are slow to roll these things out. They want to make absolutely sure that they're safe for that.